Greg Schmidt again. It's a pleasure to welcome you to the final day of the 2013 NASA Lunar Science Forum. We have another great day of talks ahead of us. I hope you're able to join us all day. I wanted to make a couple of very brief announcements before we go ahead with our first couple of talks. First of all, as we mentioned on the first day of the conference, there will be a survey that is going to be out. This will be out either tomorrow or Monday. We're working hard on this. We strongly encourage you to reply to the survey. It's very important in terms of how we conduct future lunar science forums, whether they're in person or not. So please do that. We very much appreciate that. You will note that we have had a change in schedule, as Yvonne mentioned yesterday, and we repeated at the end of the day as well. And we just have a great treat that both Bill Gerstenmaier and John Grunsfeld are going to join us at 9:30 Pacific time, 12:30 East Coast time, and give some of their views on the future of the kind of research that we all do here. So please do tune in for that. So what I'd like to do now is introduce our first speaker of the morning session, who is David Kring. David is one of our PIs, has been for the last 4.5 years for NASA Lunar Science Institute, now CERVI. He's a senior geologist, and he is at the Lunar and Planetary Institute. And today his talk is entitled "In a Lunar Classroom: Lessons to be Learned About Impact Cratering and the Collisional Evolution of the Solar System." So David, take it away.
Thank you very much, Greg. I've been asked to review some of the new lessons that we've been learning about impact cratering processes based on our studies of the moon. And I'm going to frame them initially with the NRC 2007 report called the Scientific Context for Exploration of the Moon, which is one of the guiding documents of the original NLSI. Two of the concepts identified in that NRC document was to explore the bombardment history of the entire solar system using the moon as our Rosetta Stone, and to use the moon also to study impact cratering processes in general, because nowhere else in the solar system are impact craters so exquisitely well preserved and available for study. So these are concepts 1 and 6. I'm going to begin with a few remarks about the science being done to address concept 1, but I'll spend most of the time talking about concept 6. Okay. So let's begin with studies of impact crater size distributions. I want to start with a paper by Bob Strom and others in 2005 who developed a new technique. It was actually the integration of two existing techniques, one of which is to measure the size distribution of craters on planetary surfaces like the moon. The second is to use pi scaling techniques to calculate the sizes of projectiles that produce craters of different sizes. Strom et al. Integrated those two, and by looking at the ancient cratered highlands of the lunar surface, concluded that many or most of the impactors that produced craters in the lunar highlands came from the asteroid belt. Moreover, they showed that the asteroid belt was sampled in a size-independent fashion, which implied that resonances swept through the asteroid belt to deliver those impactors to the Earth-Moon system, and that in turn implied Jupiter's orbit moved. That technique was used very recently by the NLSI postdoc, Simone Marchi, who you heard speak yesterday. He took a much closer and higher fidelity look at some of those ancient cratered surfaces on the moon and came to several important conclusions. One, that the South Pole Aitken Basin, which is the largest and oldest basin on the moon, preceded the terminal impact cataclysm on the moon. That is, it was produced by some of the accretional leftovers from the formation of the planets. Moreover, there seemed to be a shift in impact velocities that corresponded with the beginning of the lunar cataclysm, and based on his calculations, it was estimated that impact velocities essentially doubled. This is consistent with a dynamically evolving solar system, and so I'm going to just illustrate that with two graphics. This is a view of the solar system before the impact cataclysm occurred. This is when accretional leftovers would have been hitting the Earth-Moon system, including the South Pole Aiken Basin impactor. About 500 million years after the solar system formed, Jupiter's orbit moved. That caused resonances to sweep through the asteroid belt to hit all of the planetary surfaces in the inner solar system. And I think this is, in terms of big ideas, is really important because it links what we're doing on the moon to the evolution of the entire solar system, and moreover, it links with what we're doing on the moon to the evolution of the outer solar system too. And so when we talk about lunar science, we aren't talking about lunar science by itself. We are talking indeed about solar system-wide science. Okay. We've also had some very exciting sample results over the last 2 years. And I'm going to highlight one particular study done by Joy and others, where they developed new techniques to kind of find the needle in the haystack. That is, during the impact bombardment period that we've just been discussing, materials were being largely obliterated as they hit the lunar surface, but small fragments of them would have survived and been incorporated into ancient regoliths. And so these new techniques allowed us to probe ancient regoliths from the lunar surface and search for these particles. This is a diagram that illustrates the time at which some of these particles were found or incorporated into regolith breccias. And some of the punchlines of this study are that the projectiles that hit during the latter phase of the impact cataclysm seem to be rather similar, and that the diversity of impactors seem to increase with time up to the present day. Okay, now there have been other approaches at studying impact cratering processes on the lunar surface, and this now moves us really from concept 1 in the NRC report to concept 6, that is trying to understand impact cratering processes in general. There have been hydrocode modeling of the South Pole Aiken Basin, which is, as I said before, the oldest and largest basin on the moon. The first of these was a paper by Schultz and Crawford, followed by work by Potter et al. And Wazorek et al. All of them have different starting assumptions of the impactor as it hit the lunar surface. I simply here feature one of them, the results by Potter et al., which suggested the impactor was about 170 kilometers in diameter, moving at about 10 kilometers per second. And one of the interesting things is this impact velocity, which seems to produce a structure that best matches observations of the lunar crust, is half the present-day impact velocity and is therefore consistent with that earlier result that I highlighted from Marchi et al. Whoops. Okay. Modeling has also, not surprisingly, targeted the Orion Basin, the last of the basin-forming events on the lunar surface. It is a spectacular structure, as you can see highlighted here in LRO LOLA schematic. This is one of several studies of this particular impact basin. Another was done by Nam et al. That used LOLA data to look at the scarps of the outer two basin rings and confirm previous models that suggested that they were normal faults. But as a result of this modeling, she was able to say something about the depths of that faulting. And not too big of a surprise, I think, what this study showed is that Orientale formed in much the same way we believe Chicxulub on Earth formed 65 million years ago. In a study by Witten et al. From the Brown Group, a study of the Mare that later flooded Orientale was conducted. And there were two, I think, very interesting results from that work. One is that the Mare formed 60 to 100 million years after the Orientale Basin was produced. And the Mare had an extensive history from about 3.7 to 1.66 billion years ago, which corresponds in age to near-side Mare production. Now, the latest lunar data was obtained by the Grail team, Maria Zuber and her team. And one of the fascinating results, I think, of that work, which is still emerging, is that impact cratering is had a very strong effect on the gravity structure of the moon, which you can see highlighted in this comparison of the role of topography and the free air gravity structure of the moon that team produced. I'm not going to say very much more about that because at this point we can't say very much more about this. This data has just come down. Maria's team is working very hard to distill it. I will say with regard to impact cratering that one paper has just appeared by the group from Purdue, and I think many more are going to be forthcoming, especially those that focus on Orion Tally, which I think will be very important to integrate with the modeling studies that I just reviewed. Okay, that brings us then to the spectacular, if not stunning, imagery that Mark Robinson and his LROC team has been producing over the last 4 years. I want to start with this oblique view of the Tycho crater, which is just eye-popping. Here at the LPI, we had printed an immense version of this thing that stretches down the hallway of along the outer edge of the building, and we routinely run field trips to this image, and I actually encourage other faculty at other universities to do the same. It's a wonderful image to actually teach about impact cratering processes. So I'm actually going to illustrate what you can do with the image with a few slides. Okay, this is actually an image of the outer portion, the rim of Tycho, and you can see that there are exquisite details revealed in the ejecta blanket. You can see impact melt pools in the terrace zone, and you can see the normal faulting that occurred during the modification phase of Tycho's formation. Here we have an image of the flank of the central peak, which shows fractured melt blanketing the central peak. You can see a boundary lineament between the central peak and the impact melt, and you can see a host of features in the impact melt that surrounds the impact or the central peak. Moreover, here's another view of the central peak where you can see the coating of melt on the central peak, and here you can actually see the expected fracturing and faulting that occurred as that material was uplifted from depth in the Earth's crust to the lunar surface. All absolutely spectacular views, and much applause for Mark and his group. Okay, they've also captured, of course, images across the lunar surface, and I have to say that if you start looking at the images on their website, you can actually become lost and forget you have other duties. Not that that has ever occurred to me, but let me just contrast what I showed you with the Tycho complex crater with this view of Giordano Bruno, a simple crater about 22 kilometers in diameter, and just draw your attention to the floor of this crater. And I hope you can see this, but this image illustrates beautifully that impact craters are filled with complex and overlapping flows, not a single monolithic lens of debris. And this is really powerful because it is actually lending geologic reality to structures that we oftentimes have simplified or idealized in the past. Here's just another oblique perspective of Giordano Bruno, which illustrates how you can actually use this imagery to look at the uplift of crater walls and the overturning of the ejecta, which is actually a process that has been examined most recently by Buck Sharpton here at the LPI. Here's, for example, a picture that shows coherent bedrock that is exposed in the walls of the Marius A crater, and he's been able to show that those layers have been uplifted by about 600 meters above the pre-impact levels. These types of high-fidelity views of impact cratering process is going to advance greatly our understanding of these processes that thus far have been limited largely to studies of highly eroded structures here on Earth. Okay, and how can I forget the impact melts on the moon? They're everywhere. They're spectacular. Here's just a set of 4 that I've captured from a paper by Identity et al. And I'm not going to walk you through all these, but I think just you can see from the views that they're absolutely stunning, and there are lots more lessons to be learned about those impact melts. That then brings us to the current impact flux. Those all being previously the things I spoke about being ancient events. Let's talk then just for a moment about the current impact flux. There are basically two ways that have been used to study this phenomenon. One is an Earth-based or ground-based process that looks for flashes as these impact events occur on the lunar surface. The second method, again, uses the LROC capability, where they actually look for features that have appeared on LROC imagery that didn't exist on older Apollo-era imagery, for example. Okay. Now, I have to say, as spectacular as this remote sensing data is, there are a host of questions that still remain, and these are questions that are really going to be best addressed by getting back onto the surface, either robotically or ideally with crew, and surveys on the ground, and actually the collection of samples that are returned to Earth. Now, you might ask, where on the lunar surface might we begin that type of endeavor? One of the places that has received a lot of attention is the Schrodinger Basin, which is within the South Pole Aitken Basin. It's about 320 kilometers in diameter, and this is a feature that actually gained initial attention by Gene Shoemaker and his team with using Clementine data. In fact, in the lower right-hand corner, you can actually see a geologic map that Shoemaker and his colleagues, including LROC's Mark Robinson, I might add, made of the basin structure. More recently, that is in the past few years, we've had a series of studies by a diverse set of groups. Scott Mest published a paper. O'Sullivan et al. Published a paper in a similar volume with Mest, looking particularly at landing sites that might provide access to important geologic samples for return to Earth. More recently, Kramer et al. Had a paper, Kumar et al. Had a paper, Burns et al. Had a paper, and Shankar et al. Had a paper, all within the last few months. So there's simply a growing attention for this interesting impact basin. You can see in the lower right an oblique view that shows the uplifted peak ring, which rises 1 to 2.5 kilometers above the lunar surface, providing wonderful exposures of crustal lithologies that have been uplifted to the surface, which allows you not only to study impact cratering processes, but also processes that preceded the formation of this basin, and in particular, the processes associated with the original differentiation of the moon and the production of the lunar crust. At the T's, you can see in front of the peak ring is a pyroclastic vent. So missions to this particular locality not only would provide fantastic science, but also an opportunity to explore ISRU issues of interest to HEOMD. Okay, now you might ask how we got that. You might ask how we would do that, and one of the ways to do that is with the Orion spacecraft, which could be launched to the Earth-Moon L2 position, and which would work in integration with a rover on the lunar surface that could collect a sample, put it on an ascent vehicle, and return that to Earth. Moreover, we could do not only geology, we could do astrophysics, and I think I will stop there because that, I think, is going to be a perfect segue into the next talk by Justin Casper. Thank you.
David, thank you for a wonderful overview. I'm just continually struck how much our knowledge has changed just in the last small handful of years. I'm not seeing any questions online quite yet, although I did see Clive Neal typing earlier. Maybe he decided to get shy, perhaps. Did we have any? Did we have any questions from any of the hubs, or perhaps here at City Central?
I've got one.
Okay, Brad Bailey.
Yeah, great. Thanks so much for the talk, David. You showed the Grail free air Bouguer anomalies, and from my understanding, most of the large-scale impacts, you have low-density breccias underneath most of the craters, which produces a negative Bouguer anomaly. Could you talk a little bit about some of the processes that might be producing a positive Bouguer anomaly underneath these craters?
Yes, Brad. Impact cratering is complicated in that it produces both high-density and low-density materials, some of which can actually be stacked one on top of the other. In addition to fracturing rock, which, as you suggested, will reduce densities, you do produce impact melt, which can be a relatively high-density structure, and you can also uplift material of higher density from greater depth, in particular the mantle of the moon, or the mantle on the Earth if you were talking about a similar size impact event on our planet. There's also modeling by several people, including one of the LSI postdocs, Ross Potter, has shown that you also can get crustal thicknesses adjacent to the central part of the basin, which affects the gravity. And there are several other processes that I'm going to be overlooking in this very quick synopsis. But it is a little bit complicated, but it is a series of processes that you can understand and model rather confidently.
Thanks, David. And we'll take one more question, and then the rest will go online. And this one is from Clive Neal. Where on the near side would you have a robotic sample return to study impacts? Near side sample return is easier and cheaper than the far side, and given the current budget, should we target the near side first? No, I am not shy. Thanks, Clive.
Thanks for clarifying that, Clive, if it needed to be clarified. Okay, so I would steer actually towards Orion Basin. If I had to choose a location on the near side that didn't require a communication relay, I would probably go to Orion. That said, I don't think we should shy away from exploration of the far side. All it requires, and I want to put emphasis on all it requires is a communication relay. I mean, we have hundreds of comm satellites in Earth orbit. I think we can afford one comm satellite in lunar orbit, and I think that we should just push ahead and explore that fascinating lunar far side.
And I'm going to say a quick amen to that, David. Thanks again for a great talk.